give the name of the third member of the alkene homologous series. So to get the name of the alkene homologous series, we need to know the general formula of this particular alkene series. So for the alkene series, the general formula is CnH2n. CnH2n. Now, for the in this particular homologous series, n is equals to 2, 3, 4, so on. In other words, n does not begin from 1. N begins from 2. So the first member has got 2 carbon atoms. Okay? So we have got the following members. The first member, we are going to first of all write the formula and see what we are going to call it. So C for H2N. 2 times 4? 2 times 4?
8.
8. So this is the formula. The formula of the third member is C4H8. Okay? Now, we know that the prefix for, let's say, 1 is et. 2 is, for 1 is met. For 2 is et. For 3 is prop. Now we know member number 1 has got 2 carbon atoms. Number 2, so number 1, member number 1 has got how many carbon atoms? 2 carbon atoms. So member number 2 will be having how many? 3 carbon atoms. Member number 3, how many carbon atoms? 4. Member number 4, how many carbon atoms? 5. Are you seeing that? So we are looking at member number 3. Are you seeing that? How many carbons does it have? 4. So what will be the name? The name will be but. But for the prefix for 4. And then it is ending with the suffix "ene" because it is alkene. So it's not butane but butene or but1ene. It's either butene or but1ene. Are we together? The goal to be 4. We must have at least 2 carbon atoms. So to draw and name all isomers of butane. Now butane is an alkane. Okay, it is an alkane. The general formula for alkanes is CnH2n plus 2. That's the general formula for alkanes. CnH2n plus 2. That's the general formula. Whereby n is equals to 1, 2, 3, and so on. Are we together? Now we are looking at an alkane with the prefix but. So but is the prefix for 4. Butane, an alkane which has got 4 carbon atoms. So if n is equals to 4, we are going to substitute here to get the molecular formula. So it's going to be C4H. 2 times 4, 8, plus 2, 10. So the formula is C4H10. So when we are told to draw isomers, we have been told to draw all those which are having the same molecular formula, which is this formula C4H10, but what? Different structural formula. So you are going to draw all which are having this formula, but different structural formula. So the first one is the normal straight chain butane. So you draw 4 carbon atoms like this. 1, 2, 3, 4. And then after drawing these 4, we make sure that each carbon is surrounded by 4 covalent bonds. So you have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Because alkanes are hydrocarbons, we make sure that these covalent bonds which are hanging are surrounded by hydrogen. Hydrocarbons are compounds which are made up of carbon and hydrogen only in their structure. So these are hydrogens. Now, So if you look at this structure very keenly, you realize that the number of carbon atoms are how many? 1, 2, 3, 4, which is C4. H, let us count the number of hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. So what will be the name? This is now normal butane. Normal butane. Butane, which is just the normal straight chain butane. Now the second member will be as follows. We take the long chain, which is 1, 2, 3, 4. We cut. We make the long chain to have how many carbon atoms? 1, 2, 3. So we draw like this. 1, 2, 3. Like that. You fill with covalent bonds like this. We number them. So this is carbon number 1, this is number 2, and this is number 3. Okay? I hope you are following the steps. We have drawn the 4 carbon atoms, sorry, the 3 carbon atoms, which are those ones. Now one of them is remaining. Now you put a branch. The branch is not placed in the first carbon atom, nor the last carbon atom. You don't put the branch in carbon number 1 or carbon number last. Where do you put the branch? In the middle. So in the middle here, what is remaining is one more carbon atom. So you show this carbon here and you show all the hydrogens that are surrounding carbon, like that. Now what is remaining, we fill using hydrogen. All of them, we fill all of them using hydrogen. So each covalent bond to be filled with hydrogen like this. So all the covalent bonds have been filled using hydrogen. Now let's see how many carbon atoms are in this. Okay, first of all, let us give it a name. What's the name? 1, 2, 3. The branch is in carbon number 2. So you write 2 hyphen. The name of this branch, this is now the branch. What do you call that branch? It is a C3 group. Methyl. Okay. 2 methyl. 2 methyl. Now the longest continuous chain has got how many carbon atoms? 3. So that is propane. 2 methyl propane. These two are the isomers of butane. Why do we call them isomers? We need to see the number of carbon atoms which are present and the number of hydrogen atoms which are present. And then we conclude, why do we call them isomers? So here C and then H. How many C's do we have? 1, 2, 3. Plus this one on the branch. There are how many now? 4. And then we count all hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. C4H10. Are we together? So these are isomers. What are isomers? They are molecules which have the same molecular formula. Look at the molecular formulas. They are the same. What are these? C4H10. So the molecular formulas are the same. C4H10. But are the structures the same? The structures are not the same. The same. That is why the names are different. So these are molecules which have the same molecular formula but have different structural formula. That's why isomers. It has only 2 isomers, which is normal butane and 2-methyl propane. Draw a diagram to illustrate the electrolysis of molten aluminum oxide. We have got electrolysis in form 2 and electrolysis in form 4. Okay? Electrolysis which is in form 4 is especially for aluminum, is for the extraction of aluminium, is under the topic metals. Okay? So we can draw the 2. We can draw the one for form 2, which is very simple. You draw something like this. Okay? This one is the negative terminal of the battery. The longer stroke is positive. The shorter stroke is negative. Are we together? So this one is an electrode. You can say, okay, here we have molten aluminium oxide. Molten aluminium oxide. Okay, this apparatus here is the crucible. Okay, the wire which is here is the connecting wire. On top here we have the battery. Okay, what is this? Wire goes. Okay, here tripod stand. Okay, then here is the means of heat. You must have heat. If heat is not there, then the process of electrolysis may not be able to take place. Electrolysis takes place in the presence of heat, so that this aluminum oxide can become molten. Now, where is the anode and the cathode? This electrode has an N, and this other electrode has an N. Now, the electrode that is connected to the positive terminal of the battery is known as the anode. And it is positive electrode. So if you are asked, define an anode, there are two ways you can define the anode. You can say, well, anode is the positive electrode. That is accepted. But you can say, anode is the electrode that is connected to the positive terminal of the battery. Then you have this other electrode here, negative electrode, because it is connected what? To the negative terminal of the battery. So this is now known as the cathode. Two definitions for the cathode again.
It is a
Negative electrode, or electrode connected to the negative terminal of the battery. Electrode connected to the negative terminal of the battery. That is one way we can draw, and it is the easiest way. But there is another diagram for electrolysis of molten aluminium oxide in book 4. That one is also acceptable, but it is a little bit complicated. It's not like this one. This one is a very simple one. Which one do you prefer? This one. Are we together? If you don't know which is the anode and which is the cathode, in an exam, maybe you have been told, label the anode, and you don't know which is the anode. Write both anode. Are we together? Or you have been told, label the anode and the cathode, and you are not in a position to distinguish between anode and cathode, because you don't know which is the positive terminal and which is the negative terminal of the battery. Then, instead of losing the 2 marks by interchanging, you write both anode, or both cathode, because at least one of them is a what? Is a cathode. Are we together? Instead of mixing the two, and then you get a 0. Is that okay? Number 14. The diagram below represents a setup of apparatus used to study properties of chlorine water. Then you are being told to name gas X. Now, before we look at that, we need to understand that this question comes from chlorine and its compounds, which is a Form 3 question. Now, we have chlorine, our gas. It can react with water to give a mixture of two gases, of two compounds, HOCl and HCl. So we have a mixture of two acids. This is known as chloric 1 acid, and this is known as hydrochloric acid. So these two acids, when mixed together, appear yellow in color. They appear yellow in color. Now, that is due to the presence of this one, HOCl, which is also known as what? Chloric 1 acid. Now, this first equation, write an equation for the reaction that occurs. Now, on exposure to sunlight, chloric 1 acid decomposes to give us the gas that we are seeing there. So we write that equation so that it can assist us to get Roman A. So we have this equation. This is the balanced equation. Chloric 1 acid decomposes in the presence of sunlight or UV light to give us hydrochloric acid and oxygen gas. Okay? So that occurs only in the presence of sunlight. So in the presence of sunlight, this yellow color will disappear due to the composition of chloric 1 acid. To which acid? To hydrochloric acid. You see that?
Yes.
Now, name gas X. You can look at the gas. Which gas is it? Oxygen. So that's how we got this gas. Oxygen gas. In the presence of sunlight, chloric 1 acid decomposes to give us oxygen and hydrochloric acid. And the yellow color disappears. And that one only occurs in the presence of sunlight. If sunlight is not there, the reaction will not occur. Then you are told, give one use of chlorine. We have several uses of chlorine. So one of the uses of chlorine is treatment of water, what you usually call chlorination of water. Okay? Another one is manufacture of bleaching agents, e.g. this one. E.g. that one, that's a bleaching agent. Like for example, Topex, we have others like Jig. All those are examples of bleaching agents. Vim, brand names of bleaching agents. Vim, Jig, Topex. Okay, all those are bleaching agents. You can list other uses of chlorine. There are very many. Sample of 0.63 grams of lead powder were dissolved in excess nitric 5 acid to form lead 2 nitrate. Now that equation will be as follows: lead solid plus nitric 5 acid. What do you form? Lead 2 nitrate. Okay, a solution. That's what? Plus hydrogen, plus water and liquid. Why? Why is it forming water? Because nitric 5 acid is a strong oxidizing agent and it oxidizes any hydrogen that is formed to water. Let us balance this equation. Lead 1, hydrogen 1, hydrogen 2. So what do you write here? 2. Nitrogen 2, nitrogen 2 times 1, 2. Oxygen 6, 7. Okay. Now, let us just leave it like that because we are not interested in the others. What we are just interested in is the lead 2 nitrate. All the lead 2 nitrate was then reacted with sodium sulfate solution. So we take this lead 2 nitrate and we react with sodium sulfate solution. Sodium sulfate. So when we react lead nitrate and sodium sulfate, we form lead sulfate and sodium nitrate. So from that, We balance. Lead 1, lead 1. Nitrogen 2, nitrogen 1. So they write here 2 to balance the nitrogen.
Yes.
Oxygen 6 plus 4, 10. Oxygen 4 plus 6, 10. Sulfur 1, sulfur 1. Sodium 2, sodium 2. That equation is now balanced. So this is the equation. But this is not an ionic equation. This is known as a stoichiometric equation. An equation which contains the reactants and the products. Very good. So we can write the stoichiometric equation and then use the stoichiometric equation to get the ionic equation. So we copy this one the way it is. I don't want us to go through the whole process because it is a lengthy process, but I would just want us to use our eyes and see. Lead nitrate contains lead ions and 2 nitrate ions. Are we together? In the aqueous state. So we are going to remove what is in the aqueous state both on the reactant side and on the product side. Let us see. Lead is aqueous. Here lead is solid. So if there's a change in state, you don't omit, you don't remove. You don't remove. So it means lead has undergone a change from aqueous to solid. Are you seeing that?
Yes.
We come to nitrate. Now nitrate is in aqueous state, and here nitrate is in aqueous state again. So what does that tell you? There's no change of state. So you can remove the nitrate ions because they are in aqueous state, both in the reactant side and in the product side. In other words, they have not taken part in the reaction. They are just spectating. They are spectators. Just like players in the field. Just like what? Observers. Spectators in the field. So you remove nitrate here and nitrate there. Let's go to sodium. Sodium is in aqueous state. Sodium is in aqueous state. So again, sodium is a spectator. We omit the spectator. We remove the spectator. So we remove sodium here and sodium here. Sulfate, aqueous. Sulfate, solid. So that one has undergone a change. So we write what is remaining. Now what is remaining is this lead. So we write lead 2 ions in the aqueous state is combining with sulfate ions in the aqueous state to form lead 2 sulfate in the solid state. So this is the ionic equation that was expected of you. What you need to remember is this, that you need to have a summary of solubility of all salts. Solubility of all salts. Like for example, you can say all sulfates are solid. All sulfates are what?
Solid.
Except only 3 sulfates. That is what? Lead sulfate, which is this one. Are we together? Yes. Barium sulfate. And which other sulfate? Calcium sulfate, which is slightly soluble. Are we together?
Yes.
How many sulfates are insoluble?
3.
Only 3. The sulfate of lead, calcium, and barium. But that one of calcium is slightly soluble. So this is why we are saying this is in solid state. We move to the next question. Determine the mass of lead solid formed in the reaction in A above. Now this lead sulfate here. So what will assist us is the mole ratio. Okay? So we have mole the mole ratio of lead sulfate to lead ions is 1:1. So we are going to use information that we have to get first of all the number of moles of lead. So the number of moles of lead will be obtained from this 0.63 grams of lead. Okay? So when you get the number of moles of lead ions, of lead solid, that is the same number of moles of lead ions. Are you seeing that? So we'll come here and say moles we say number of moles of lead is equal to mass in grams, we divide by molar mass. The mass is 0.63. The molar mass is 207. What will be the number of moles? 0034. Moles of what? Of lead. What about moles of lead sulfate? We'll use the mole ratio. We'll come and see if 1, which is 1 for lead ions, is the same as 0.0034 moles. What about 1 for lead sulfate? Will be what? So this one will be 1 times 0.00304. We divide by 1. We must show the working, even if we are sure that the answers are the same.
The same.
Very good. So the answer of lead sulfate will be 0.00304 moles of lead sulfate. Now we convert these moles into mass. How do you get the mass? So mass in grams is equal to moles times molar mass. In other words, we are formulating this formula. We are making mass the subject of the formula. We multiply both sides by molar mass. So what is the moles? 0.00304. We multiply by molar mass of lead sulfate. How many atoms of lead do you see here? 1. Okay? Times the relative atomic mass of lead, which is what? 207. We add, how many atoms of sulfur do you see? Only 1. Times the relative atomic mass of sulfur, which is 32. We add, finally, how many atoms of oxygen? 4. Very good. Times the relative atomic mass of oxygen, which is 60. Now the answer we get there, we multiply by 0.00304, which is going to be what? The answer is 0.9222 grams of lead sulfate. I hope you have followed it keenly. The mole ratio of lead ions to sulfate ions is 1 to 1 to 1. We are not interested in the sulfate ions. We are interested in lead and lead sulfate. The mole ratio of lead to lead sulfate is 1 to 1. Okay? How do you get the moles of lead ions? From the moles of lead metal. Because the lead metal was dissolved using nitric 5 acid to give us the lead ions. So you just say 0.63, we divide by 207. We get the number of moles, which is 0.00304. Then you relate using the mole ratio. If this one is 0.00304, what about the other one? You show by cross multiplication, but the answers are the same.
The same.
What about mass? You formulate. If moles is equals to mass divided by molar mass. What about mass? You multiply by molar mass both sides, and therefore mass in grams will be equals to moles times molar mass. How do we get the mass? We get the mass by summing the relative atomic masses of all atoms which are present inside the compound. Like that is the molar mass of lead sulfate. It will be the mass of lead plus the mass of sulfur plus the mass of oxygen in the compound, which you are going to get is how many? 303. When you multiply, you get 0.922 grams, and that will be the mass of lead sulfate.